In B, we already have an expression for the adjustment coefficient, and then we want to find the reinsurance proportion that maximizes the adjustment coefficients and in turn minimizes the ruin probability. We can also say that what we want to do is we want to find the optimal reinsurance level. So we want to find the A that maximizes R. One thing that is quite useful to note, also if in some not so distant future you try to maximize R in some other case where you have some other claim size distribution, is that we know from a reference in Hans Schmidli on page 47, I think he refers to some other book where there is a result that says that in the Kremer-Lundberg model, for any claim size distribution where the adjustment coefficient exists, the adjustment coefficient is unimodal, which means that you can find the extremal value of R by differentiating it with respect to this A, and is unimodal in, I should write in A, So you can find the maximum by differentiating R with respect to A, and then setting that equal to 0 and figure out which A in this interval satisfies that equation. So that is what we will do. We will differentiate R with respect to A and set that equal to 0 and solve for A. So first, we will find the derivative of R with respect to A. So the derivative of R with respect to A is just equal to theta multiplied by the derivative of 1 over 1 minus A. Now, the derivative of 1 over x, just recall that, is equal to minus 1 over x squared. So what we want is we will take the derivative of this is 1 over 1 minus a squared, and then you have to multiply by the minus, but then you also have to multiply by minus 1 since that is the derivative of the inner function 1 minus a. And then we subtract by the derivative of this fraction here, where again you have 1 divided by the entire denominator squared. And then you want to multiply by a minus 1. And apart from that, you also want to multiply by the derivative of this inner function. And the derivative of that is given as minus 1 plus psi r. And then we can actually see, what do we have? We have a minus here that cancels with this minus. You have a minus here that cancels with this minus. I should also just put a parenthesis here. So the derivative of r with respect to a is given as theta multiplied by 1 over 1 minus a squared minus 1 plus psi r divided by psi minus psi r. Did I forget the r up here? Yeah. Plus 1 minus a multiplied by 1 plus psi r squared. And now we want to solve for a in this equation where we set this expression equal to 0. I think the easiest thing to do is actually to solve for 1 minus a first, since you have 1 minus a here and 1 minus a here, and then isolate a in the resulting expression afterwards. So solve for 1 minus a in the equation where we set this entire expression equal to 0. So what we want to find is we want to find the 1 minus a which satisfies that 1 divided by 1 minus a squared should be equal to 1 divided by 1 plus psi r divided by psi minus psi r plus 1 minus a multiplied by 1 plus psi r squared. And that holds if and only if, and let's just multiply both denominators over on the other side, so we cross multiply and then divide over by 1 plus psi r, then we get that we must have 1 minus a squared divided by 1 minus a squared should be equal to psi minus psi r plus 1 minus a multiplied by 1 plus psi r squared divided by 1 plus psi r. And you can see that this starts reminding you a bit of a quadratic equation. So let's just write that up on the shape of a quadratic equation. Should we move stuff one way or the other way? Well, that's completely up to us. So let's just move the 1 minus a squared over to the right hand side. I think that's easiest. So you have 0 should be equal to 1 minus a squared multiplied by, well, which coefficients will we have? We will have the 1 plus psi r squared divided by 1 plus psi r. And apart from that, since we subtract the 1 minus a squared and move it over to the right hand side, you will also have a minus 1. So this is the coefficient for the squared term. And then you have the linear term where it's 1 minus a. And the linear term you get by multiplying this squared expression, by unraveling this squared expression. And what you get, it will be 2 multiplied by 1 plus psi r multiplied by psi minus psi r. And then you also want to divide by 1 plus psi r. And lastly, you have the constant term, which is just given by psi minus psi r squared divided by 1 plus psi r. And that is equal to 1 minus a squared. And you see some things cancel here, right? The squared cancels with the denominator. This cancels with the denominator. So basically what we have now is a quadratic equation where the first coefficient is given by psi r multiplied by 1 minus a squared. And The second coefficient on the linear term is given by 2 multiplied by xi minus xi(r), multiplied by 1 minus a. And the last coefficient on the constant term is xi minus xi(r) squared divided by 1 plus xi(r). I mean, basically, we're just doing high school maths here, which actually also is one of my it's kind of my Achilles heel, this kind of calculation. I can never get these calculations right, so I apologize in advance if there are errors in these calculations. Anyways, we want to find the 1 minus a that satisfies this equation here, and for that we will use the standard the roots of a quadratic equation satisfy this thing here, where the a and b and c just stand for the coefficients that are on the quadratic, linear, and constant terms. So let's just use that to figure out what the values of what the roots should be in this quadratic equation. So 1 minus a should be equal to minus the coefficient on the linear term, which is 2 xi minus xi(r), and then we have plus minus the square root of something that's quite long. So you have b squared, which is this term squared. So you have 4 xi minus xi(r) squared minus 4 multiplied by the quadratic term's coefficient multiplied by the constant term's coefficient. So it's xi minus xi(r) squared divided by 1 plus xi(r). And you take the square root of this entire thing, and in the denominator we have 2 multiplied by xi(r). And one thing that we can do already now is you can see that in the first term here you have 2 multiplied by xi(r) minus xi, if you just multiply the minus in, and then you divide it by 2 xi(r). So what you get is 1 minus xi divided by xi(r) for this first term. And then we have plus minus, and now let's just throw the denominator under the square root as well. And if we want to do that, then we need to square the denominator as such, and then you see that there are some things under the square root that also kind of cancel out. So which things cancel out in the square root? The 4's all cancel, and that's pretty nice. And apart from that, what else do we have? Well, let's just try to continue our calculation a little bit. Here we have a 1 minus xi divided by xi(r) plus minus, we have a rather long square root. And in this first one here, what you get is, well, xi minus xi(r) squared, which you can actually take outside of a parenthesis, and then inside you can have 1 minus xi(r) divided by 1 plus xi(r). And in the denominator, you get, what do we have? Just move the square root down here. You have xi minus, you have xi(r) squared as such. And this is quite nice because you can see that the square root of this expression here can be easily taken just by removing the squares. And then what you have is 1 minus psi divided by psi r plus minus 1 minus psi, well, what do we have here? You take the square root of this thing, so you have psi minus psi r divided by psi r, and you multiply by the square root of 1 minus this fraction, which is also just the same as 1 divided by 1 plus psi r. Now, this thing here is equal to psi divided by psi r minus 1. And when you get the plus minus on, you can just take this outside, and the expression is equal to 1 minus psi divided by psi r multiplied by 1 plus minus the square root of 1 divided by 1 plus psi r. So recall that I started out by saying that there is only one solution that yields the extremum of r, and that is because you need to take into account that there is a constraint on a due to the net profit condition. So we have that so we need to recall our constraint on a, that a lies between 0 and psi over psi r, which also means that minus a lies between minus psi over psi r to 0, which also means that 1 minus a should lie between, well, 1 minus psi divided by psi r to 0. And what that means is that what just happened here is, am I just being silly again? Oh, not to 0. Sorry, that's why. Here, 1 minus a should lie between 1 minus psi over psi r to 1. Sometimes you look at the screen and then it just kind of, like, you know, moth drawn to a flame. You get a bit confused. So we require 1 minus a to be greater than this value here, which also means that we must then multiply it by something that is greater than 1. So in our case, we have, due to the net profit condition, that 1 minus a must be given as this here. So the case where we have a minus simply does not satisfy the net profit condition, therefore we cannot use that case. Okay, so we have now an expression for 1 minus a, but what we wanted was to find the value of a that maximized r. So now write up a, and that's quite easy because since 1 minus a is equal to this, we can just note that 1 minus a is equal to 1 minus, well, what do we have? Psi divided by psi r. So now we've taken care of these two multiplied with each other and these two multiplied with each other, and now let's consider these two multiplied with each other, which is just the square root of 1 divided by 1 plus psi r multiplied by psi divided by psi r. And then the last one we need to take care of is this 1 multiplied by this term here. And that gives a plus, but we put it under a minus sign, so you need a minus 1. So 1 minus a is the same as 1 minus this entire expression. In conclusion, a is equal to psi divided by psi r plus the square root of 1 over 1 plus psi r multiplied by psi divided by psi r minus 1.